I'm going to compete with lunchtime, right? Paul Duvoy, Colin Krieger, myself, and Jerry Johnson, analysis of bevameter regolith interaction mechanics using the COUPi discrete element method. The bevameter is a device that was developed to actually study mechanical properties for vehicle mobility. So it actually consists of two tests. One is the sinkage test, when you press the flat plate into the regolith, and that's supposed to simulate the normal load on the wheels, and also a shear test when you actually rotate the shear ring on the bevameter to receive the shear load on the wheels. So the specific of this test that bevameter area size need to be of the size of the wheel of the track. So when you change a wheel, you need to also change a plate to correspond to that. This is a place where DEM analysis can be very useful. So you can scale the numerical experiment much easier than when than replacing the real plate. Besides, of course, all other advantages of DEM, that you can actually do your simulations in the conditions not present on the Earth, and also see what's going on inside. So, we're developing a COUPi discrete element method. You can see a little logo here. This model was developed as a part of NASA Lunar Science Institute project, and it can model interactions between like big set of particles of different shapes, and you can compose the shapes from like different geometrical subshapes, and you can also model polyhedra, including concave shapes, and see the interaction between them and the machines. So it has a computational core, and it also has a scripting layer, and you can actually make different experiments without changing the computational core. Very user-friendly, a lot of documentation, and very extendable by writing new scenario scripts for the model. There are physical parameters that actually affect the simulation, and you can see that mind map I plot here for. So the particles, particle contact friction, specific gravity, shape, size, elastic properties, surface energy parameters. Then you also have physical parameters assigned to the regolith, like bulk density, particle size distribution. And also, you can change different simulation parameters and see how they affect the simulations. And we did a lot of testing, and we can control these parameters in the DEM. So the goal is to find the physical parameters that actually correspond to particular soil or regolith, and then compare and validate the model with the experiment, and be able to actually to do the testing for the conditions that we can't actually simulate. We can actually make an experiment for. So this is a summary of what we did for the bevameter test. So one of the features of the model that you actually can take the CAD model from computer model, import it into the discrete element method model, and do the simulation with exact tools that you have. Then you can that what we do is we compare that measured result from laboratory bevameter test and COUPi simulations. So this is an example, or this is an image cap and a sharing from NASA Glenn Research Center, and this is a direct import from the manufacturer's step model into the COUPi discrete element method. So same with a flat plate. This is the setup at NASA Glenn Research Center, the bevameter, and on the left you can see the picture of the flat plate for the sinkage test. So now about the particles. So we do some log normal particle size distribution. We also use, in this particular work, we used a very simple particle made of 3 spheres. This configuration was suggested by Alan Wilkinson from NASA Glenn Research Center. When you connect 3 spheres, they have only one single common point, all 3 of them. This shape is very easy to compute, computationally very efficient. From other side, it actually represents some sophisticated behavior of the soil when you have like interlocking between particles. And also, as I mentioned before, it has also very nice analytical formulas for moment of inertias and other things that you need for the simulations without doing it numerically. This is a sinkage test simulation, and it will show actually, let me run it. So you can see the force chain. This is just a slice of 3D simulation. There is a big domain filled with this particle that I mentioned above, and you can see the force chain that formed during the sinkage test here. So here is a pretty shallow set, and on some stage you are going to have the bottom effect. So we probably will see the resistance probably will collapse at the end of the test here. This is a pretty dense material, so you can see that there is a pretty big influence of the bottom here. This is the shear test, the bevameter placed on the same soil. And so first it's pressed with under the constant load into the regolith, and then it twists. Probably you won't see it because it's also just a slice, but then it starts rotating in this direction. So you can see the build-up around and also the force chains. This is a little comparison. This is just, we are just on the stage when we try to find the real soil properties of grain-grain interaction. So you can see that the pin line shows the sinkage test for pretty dense material, the bulk density, the highest bulk density among all the tests. So actually, the tip resistance, that's not like plate resistance, actually grows with increasing bulk density. And the blue line is the sinkage test that you saw on a movie. So it goes to some level and then behaves a little bit different at the tail, probably because of the bottom effect. Like a red line is simulation of the bulk density that's represented on the light blue line here. I'll probably skip a couple of other results here. They are, we're still working on finding the right properties for the grain size. So this is the shear test. You can see it's much lower. And I think this is because of the particle shapes are rounded. And so the shear test shows lower results. But also, we still need to find like a right particle-particle friction parameters here and right distributions. So that's where actually the right, finding right shapes for the particles is important. And we do computer tomography scans of different lunar simulants. Here is a GRC-3. We're doing it for GSC-1A and for GRC-1. So we have these shapes, of course, for like, we can import this from CAD also, but it has too many features. It's very hard to simulate. So what we're going to do is we're going to make a sort of library with similar shapes, but that would have less number of features, so some polyhedral particles, and do the simulations with them. So we do other tests, and this is one of the tests that you can see on our poster number 16 here. I'll just show it because, yeah, so it will show, it shows nicely that the force chains in the grains. This is a pretty dense packing of the regolith. Another test that we're doing to determine the properties of the particles is the Triaxial test, and we have that's a membrane around that's simulated by mass spring mesh, and so this is just a standard Triaxial test that we have. You can see that how it breaks here. So that's pretty much it. I would like just to say that we probably witnessed a very interesting time when the computers reached that pretty high productivity, and we can actually model really big ensembles of particles and start modeling complicated shapes. And probably we're probably going to see the usage of DM will grow tremendously in the next time. So that's it. Thank you very much. Yeah, lunch is soon. Oh.
So just to clarify that I comprehend what I just heard, every little grain in that box has the complexity and the faces and this.
That's right.
And then you calculate, I don't know, 1 million of those with all the contact points and all
that's
the.
Right. That's right. So
wow.
that's what I'm trying to say. That you probably remember that in 70s and 80s we witnessed like the tremendous change in the application of like finite element method or finite volume method, because computers became capable of managing the computation, like amount of computation necessary for that. I think currently we are approaching the time when discrete element method actually reaches also this moment. So there is a huge theory done in the last 30 maybe plus years, but I mean currently we get means also to perform the simulations on really on the scales necessary to produce some practical results, I guess.
You did these on actual physical tests, did you not? You showed the test equipment that you used?
Right.
What was the makeup of the particles in those tests?
Oh, yeah, that was GRC-1 lunar simulant.
Okay, so you never had a simulant that was just spheres or anything that was really close, the particle size was all the same?
There were a few tests, and one of the articles is Utah Hopkins, I think it's 2006. I don't remember but I can send you a link. Then they use like big spheres and do cyclic low Triaxial test and compare it with DM analysis. And this current model, COUPi, is actually in some extent a successor of a Corel model that was used for that test. So of course, that's a good calibration when you really can take exact big particles, exact shapes like spheres. You can measure all the contact properties and put all together and compare with the experiments. Yeah, that's nice, and that was done, and we will continue, of course, to do it to calibrate the models and validate it. Yeah, but there are papers published. Okay. Thank you.